I don't know if I think the time is already up, but I didn't hear that. I didn't hear the ring. Okay, but anyway, let's get started. Okay, so last lecture we talked about points, right? We talked about how to process point in like a high dimensional space, not necessarily two-dimensional, but also high dimension. Okay. In particular, we talk about like how to find a point. Okay. I mean, if you want to query a point, okay, query some point, okay, using like a range query in for a set of point in like a high dimensional space. Okay, we start from like a one-dimensional situation, and then to generalize to like a two-dimensional and then multi-dimension. Okay, and we talk about KD tree and the range tree, right? So today we are going to continue that topic. In other words, we are going to continue talking about the point. Okay, the problem about point. Okay, but now, okay, we are going to talk about the relationship between point and faces. Okay, this is perhaps one of the well-known motivated problem. Okay, let's say we have a subdivision. Okay, we have subdivision, or put it another way, we have a map. We have a map. Okay, then the planar point location problem, okay, is to store S, okay, this planar subdivision, which is like constructed by n edges. Okay, we want to store this planar point location. Store the subdivision, okay, in a way that we can always answer the following question very efficiently. Okay, what is the question we want to ask? Okay, given a query point Q, okay, take a closer look. This Q is any point, any query point. Okay, so we don't know the query point location in advance. Okay, we only know the subdivision in advance. Okay, so we want to store this subdivision in a way that, okay, when we are given an arbitrary point Q, we want to report the face that, I mean, in S, of course, that contains Q. Okay, this is like a very frequently used application. Okay, for example, like when you are doing like navigation, when you are using navigation system, the first thing is to find where you are on the map, right? So basically, like the first thing, okay, I mean, for the navigation system, of course, a navigation system has consists of two parts. The first thing is to find where you are. The second, as well as like where the destination is, of course, right? The second thing is to find a path that goes from your current location to a destination, right? Okay. The second part is if actually, I mean, you guys should have learned that from maybe data structure or algorithm class, like which is like the Dijkstra. Okay, Dijkstra. So assuming like you have learned Dijkstra from algorithm or data structure class. So here we are trying to answer the first part of the navigation system. Okay, how do we find where you are very efficiently, okay, given a map which is constructed by n edges. Okay, so so it will be something like this on the left hand side, right? Something like this. So when you are given a point, we want to find like which face we are located in, okay, very efficiently. So one intuitive approach is that, okay, we can induce like a vertical lines, okay, from all vertices in your subdivision. Okay, so it will cut your map into something like this, right? So it's something like your map will be broken into a lot of, we call this slabs. Okay, strip. Right, street, like something like this, right? Okay, of course, you might wonder like, well, how about like if we have 2 points, 2 vertices that happen to have the same x coordinate? Okay. Let's not worry about that. Like we call that degenerate case. Okay, we call that a degenerate case. So let's not worry about that degenerate case for now. Okay, so all vertices, we assume they do not share the same x coordinates. Okay, at the end of this chapter, okay, we are going to discuss a method, a general method that can help to solve this degenerate case. Okay, so basically, okay, let's say, okay, if we try to induce a vertical line from every vertex, then it's going to cut your space into a number of slabs. I mean, each of them will look like this, right? And okay, you could, okay, based on because when you are given this number of slabs, you can certainly represent, the left and the right relation, okay, of all these slabs by a binary search tree, right? A binary search tree. Okay, where, let me put it this way, okay, each leaf node will point to one of the slab. Okay, and the internal node will store, for example, the leaf node is going to store, the middle line that breaks this slab into 2 roughly equal half, right? So that's the middle line. Okay, and then, okay, for the left-hand side, you try to find the middle line. Again, it will break your space on the left-hand side into 2 parts. right? And so on. So you can easily construct a binary search tree such that when you are given a query point, you can use the x coordinate of your query point and this binary search tree to easily find the slab that contain that point, right? Right? It's basically just binary search tree, very simple, right? Okay, so far so good, right? Okay, because it's in the middle, in a internal node, you just store this vertical lines, okay? And then, okay, say now you locate one of the slabs that contain your point Q. Okay, you need to find like which region that Q belongs to, right? You could. Okay, remember we are given this ahead of time, right? This is fixed. So we can get this one. Okay, we can pre-compute to get this one. And once we get each of these, we can also do something similar to binary search tree, right? You can find like you can use like one of the a segment to break this slab into two roughly equal halves, right? And then, for example, for the top part, again, you try to find from here, say. You try to find another segment that breaks the top part into, half, again, and so on. But now, okay, of course, in your binary search tree, the leaf node will store the face that is corresponding to each of these regions. And the internal node will be these segments. Okay, the internal node will be the segment. And remember, I told you like we are given a query point, right? So we use the x coordinate of the query point to find the slab, right? Now we can use not just the y coordinate. We use the x and the y coordinate of that query point. For example, say this is the middle segment. Okay, say this is the middle segment. Okay, this middle segment, as I said, is stored in the root of your binary search tree, right? So you just compare this segment and your query point to see the query point is above this segment, below the segment, or happen to be on the segment. And then you know where to go, right? Okay, if it's above this segment, you know you should go to the, let's say, right subtree. If it's below this segment, we know we should go to the other subtree, right? So this is, it's not exactly you just use the y coordinate to do the job, but you can use the x and the y value of your query point to easily compare it with like one internal node which store one of the segments here to see if that query point is above or below that segment. And from there, okay, from the result, you know where to continue, visiting, going to visit like a binary search tree of this slab. So of course you have this binary search tree pre-constructed before the query is executed. Okay, you have a binary search tree for all the slabs, and you have one binary search tree for each slab. Okay, so this is good. I mean, because why? Because think about this. okay, the computation to find like which step contains that query point, you know, take a log n amount of time, right? And the computation to find like which region in a slab contains that query point also take log n, right? So it's going to be 2 log n. Well, the result is log n. It's pretty good, right? Pretty good. You couldn't expect better than that, right? Okay, so this is like a good approach, okay? But we have an issue. So the query complexity is great, it's wonderful. But if we start looking at the storage complexity, okay, the storage complexity could be as bad as n squared. Okay, why? Here we, you know, intentionally construct a special case for you to see. Okay, you can see that. Okay, remember, we assume this plane subdivision, this map, is formed by n edges. It's formed by n edges. So, is it possible to use n edges only, but to create like a, you know, n, you know, big O n squared, this many, you know, small regions that you need to store in a resulting binary search trees, in all the resulting binary search trees. Yeah, it's possible. So you can see here, okay, we have a bunch of you know, straight line edges, but the only one special case is here. Here we have you know, approximately, you know, n divided by 4, this many small edges, okay, and the rest of the edges will look like this. And because of these small edges, okay, and remember we try to induce vertical lines, right? So the result is going to be something like, okay, we actually, you know, it's going to have, you know, n divided by 4, this many slabs. But each slab, okay, because of the horizontal edges, okay, we are going to, each edge will end up having approximately n divided by 4, well, small regions. So when you multiply, because each slab will have this many regions, so total region will be n squared divided by 16, which is obviously big O n squared, right? Okay, so this is, well, we don't like it. We don't like it, okay? Because, you know, in computational geometry, we don't like anything that has a complexity that is higher than linear. Especially, I mean, if it's n log n, we can take it, but if it's like n squared, that's really too much for us to take. Okay, but, okay, when we say this approach is not good because of the cost of the storage, keep in mind that this, nevertheless, is still a good approach. When the storage space is cheap, Okay, for example, nowadays we know like a hard drive, space is so inexpensive, right? Okay, and if that's the case, you want to remember like even in the last chapter, okay, we try to use more space to exchange for a better query time complexity. Remember that? The range tree example? Okay, we pay more storage cost for to reduce the query time complexity. Okay, in the case of the range tree. Okay, but still, okay, let me point out the range tree. Okay, when we increase the range tree storage complexity, storage complexity, I mean, it's not as bad as n squared. Okay, it's not as bad as n squared. Okay, that's the first thing I want you guys to understand. The second thing is that, okay, in the case that you really want to pay this much price, okay, I mean, this much storage to get this good, query complexity, there are situations you may want to do that. You may want to do that, okay? But the second thing you need to think about is, remember at the beginning, what question I used to motivate this problem? Navigation, right? Navigation. I mean, if the navigation is done by the backend servers, then obviously you don't need to really worry about storage, right? Because backend server has a lot of storage, right? So this approach may be okay, But like I don't know how many of you drive a car. I mean, if you have chance to drive a car, and like for example, like some like a company manufacture like a navigation device, right? Such as Garmin, right? The navigation device is pretty much embedded system, right? It's an embedded system, right? So because it's an embedded system, so the storage is also limited. Okay, in case like that, okay, you really don't want to pay this much for storage. Okay. So let me rephrase. Let me clarify my point. Okay. There are situations this approach is good. When this approach is good, it's when you are using, desktop, okay, server to do this problem. Then, as I said, the storage is never an issue. Then you may tempted to use more storage, such as n squared storage complexity to get a very good. You couldn't be better than that log n query time. Okay, but if you are talking about building this capacity in an embedded system, okay, then this storage cost is too much. Okay. Any question? I saw like some students raise their hand. No? Okay. So the previous idea doesn't work. Okay? I mean, at least for the embedded system. So what do we do? Okay, this solution, I mean, I probably would just directly introduce it, because I'm pretty sure if you have taken, even if you have taken data structure and algorithm class, okay, you probably have never seen this type of data structure before, okay? We call this solution trapezoidal map. What is trapezoidal map? I mean, what is this word trapezoid? I mean, most of you guys learn mathematics in Chinese, right? In Chinese, 中文. I mean, so you don't know what this word means. This is very simple. It's 梯形. You know 梯形, right? Okay. So trapezoidal map in Chinese is 梯形图. Okay. So we basically are using the same example. Okay. But now we have we will put this subdivision actually in a bounding box. That's the first thing we need to do. Okay, which is common practice. It's a common practice anyway. Okay, that's the first thing. The second thing is, remember I told you we try to induce a vertical line from every vertex, right? In here, the same idea will still be used, but now, okay, when that vertical line hit a certain edge, we stop. Okay? So that will result what happened? It's dead. So that result in this trapezoidal map. So you can see, for example, here, for every point, we still induce a vertical line, okay, on both sides. But that vertical line will stop as soon as, it hit another edge. We try to do this to decrease the number of regions. Okay, because previous approach is good, but we end up having too many regions, right? So now, when this vertical line hit an edge, okay, we stop cutting it, so that we hope that by doing this we will, have fewer number of regions, and which will help us save the storage complexity. Okay. There's two important assumptions here. The first one, we assume. Remember, this subdivision. I told you the subdivision is formed by n edges, right? Okay. So now we assume these n edges are not crossing. Okay, they do not cross each other. Okay, they could, connect at the endpoint. Okay, your edges here could be connected at endpoints, but we do not assume they cross each other. You may wonder, how about if we do have a crossing? What do we do? this restriction is obviously too much to ask, right? I mean, in a map, obviously you have a lot of crossing, right? If you have a crossing, you just break the original edges. Originally, we have two edges that cross each other, right? Now we introduce another vertex at the intersection, so that the original two edges will become four edges. That's very easy to do, right? That's very easy to do. I mean, in the doubly connected edge list, we are going to store your subdivision in that manner anyway, right? If there is a crossing, I mean, we are going to, we are going to break, like, we're going to have a vertex at the intersection anyway, right? So this shouldn't be an issue, okay? I mean, so that non-crossing assumption, even though it looks unreasonable, but actually it's manageable. It's much easier, much easily manageable than you may think at the beginning, okay? But the second one is what I mentioned earlier, okay? We assume no two distinct endpoints of segments in S have the same x-coordinate. Okay? So this is a very important assumption. Okay? The first assumption can be easily taken care. Okay, so I will not, address that assumption. But for the second assumption, we are going to dedicate some amount of time to discuss that, how to resolve that issue. Okay, so so we call the situation of a subdivision that satisfies this this assumption to be the subdivision that is in what we call general position. General position. Okay. So now, okay, so you can see, okay, this is the bounding box. I mean, the bounding box is represented here in this example by the dotted line, and you can see each of the region actually just look like a trapezoid, right? Because, well, the left side and right side are parallel, right? The left side and right side must be parallel because the left side and right side are formed by those vertical lines anyway, right? So there are few special cases here. Okay, you can see, for example, okay, the leftmost trapezoid is actually a rectangle, right? Okay, but it's okay. Trapezoid could be a rectangle, right? I mean, you learned that in your elementary school, right? Hopefully. Okay. The other special case is some trapezoid happen to be a triangle. This case happens when some edges are connected, okay, at a certain point, right? Okay, such as this situation, this one, okay, this one. You can see quite a few examples in this one. But in that case, we consider it is also a trapezoid. It's just like one side of the trapezoid vanished, okay, which is supposed to be parallel to the other one, but the other one, I mean, the length happened to be 0. Okay, that's a special case trapezoid. Okay, we still call it trapezoid, even though it looks like a triangle. Okay? So, for a trapezoid, okay, something like here, okay? So we consider there are 4 sides. There are 4 sides, okay? So a trapezoid, okay, there's no signal that I can represent trapezoid, so I just use a, triangle, okay? So that trapezoid, triangle trapezoid, okay, try to imagine this is trapezoid, okay, even though it's a triangle, okay? It's uniquely defined by the segment top, okay, top of trapezoid, which must be an edge. And so it's a segment, okay, top segment, and the bottom segment, okay, the top and the bottom segment must be the segment that two of the n segments that we talk about, like that forms the subdivision, okay? And also we have left end point, okay, we call it left P, and right end point, right P. In this case, it's this one and this one. So you can see that there are situations that, sometimes the left, one of the endpoints may be, on the side, or sometimes the endpoint may be at the bottom or at the top of your side, okay. But you can see that, okay, a trapezoid, okay, the top one and the bottom one are segments. The left side and right side are determined by, should I say point? I should say vertices, okay, the vertex or endpoints of the some endpoints from the segments, okay. So this is true. This is true, even in the case of the degenerate situation, such as the triangle situation. For example, you can look at here. This is a triangle, right? So you can see the top one, bottom one are formed by segments, right? And the left side point and right side point, we have those here, okay? If it's not, even when it looks like a triangle, but we still have all these 4 elements, okay? Here, we call that bounding box as R, okay? We call that bounding box as R. And by the way, the bounding box, okay, so for example, like here, okay, this is a trapezoid, as I mentioned, even though this looks like a rectangle, right? So we have left side, right side, okay, which are formed by the vertical lines, right? Okay, but this, in the case of the bounding box, the top and the bottom, okay, it doesn't come from the original segment, but we can consider the bounding box, the top and the bottom bounding box as the additional segments, okay, special segments, okay. So those segments still contribute the top and the bottom of this trapezoid, and you can see the point for the right side, but there is no point on the left side, okay. So that's the same thing goes for the rightmost trapezoid here. Okay, we have a point for the left side, but we don't have a point for the right side. Okay, that's the only special cases. Okay, the only special cases on the leftmost trapezoid and rightmost trapezoid, which must involve with the bounding box. We don't have, we don't have one of the endpoints, one of the side point. Okay. So that's a special case. Other than that, everything should follow this stuff. So far so good? Okay. So let's take an even closer look at this trapezoid boundary. Okay. Let's now, okay, in particularly look at the left point. There are four situations that left point can appear. The left point can be a connection of two segments. It could be the endpoint of this. The connection of two endpoints. Connection of two segments. Okay, like the case A. Or the left point could be contributed from the top segment. Or the left point could be contributed from the bottom segment. Or left point could be contributed from another segment, but this segment is neither the top segment nor the bottom segment, right? Okay, but it is contributed by the right endpoint of another segment. Okay, look at here. Okay, except this case, all these three cases, the left point is contributed by either the top or bottom segment left endpoint, right? Okay, the similar situation can be said for the right endpoint. By the way, there are also these four cases for the right endpoint. For the right point, okay, the right P. Okay, just want you guys to understand this, because we are going to use this observation, okay, this fact, in a later discussion. Okay, to be honest, okay, today, okay, it's probably not that difficult to understand the algorithm, okay, or the what we are doing, okay, in the algorithm. It's probably not that difficult to understand. But, okay, you will find that we are going to spend more time on the proof, okay, on the proof of the the complexity of the algorithm. Okay, and this is also very important observation. Okay, we don't have this. If we don't have this observation, we will end up having some issue. Okay. So two trapezoids, okay, are adjacent to each other if they share a vertical edge. Okay. So for example, you can see this triangle, or I should say this trapezoid. This trapezoid is neighbor of trapezoid 1 and trapezoid 3, as well as trapezoid 2. Okay, we don't consider this trapezoid a neighbor of trapezoid 5 or trapezoid 4, by the way, because they are neighbor if they share vertical line, not top segment or bottom segment. Okay, okay, we only consider left-right neighbor relation. Okay, and once you understand the definition of this neighbor relation, you will find that, okay, if the set is not in general, is in general position, if the trapezoidal map was obtained from the subdivision that satisfies the general position, then you will find that, okay, each trapezoid can have at the most, two neighboring trapezoids on one side. So you can see this case. This trapezoid, it has two neighbors on left-hand side, right? This is not a special case, okay? So for example, you can see this trapezoid has two neighbors on the right-hand side, okay? Of course, a trapezoid could possibly have only one neighbor on one side, okay? I'm saying like up to two neighbors on one side, okay? So, but if the endpoints are not in general position, for example, this is a situation when you have multiple points that share the same x-coordinate. And when you try to draw a trapezoid out of this subdivision, you will find that, for example, the case, this trapezoid obviously has more than two neighboring trapezoid on the left-hand side. And this situation is really caused by, the issue that, you have like multiple endpoints that share the same x-coordinates, okay? And this is, we want to avoid this situation, okay? Why do we want to avoid this situation? Because this situation is going to create some issue in the query process, So we have this restriction that no two endpoints have the same x-coordinate. Okay, we will tell you how to remove this restriction later. Okay. So this situation is not possible. Okay, if our second assumption holds. Okay. Okay. So here comes the interesting part. Okay. What time is it? Oh, it's already break time. Okay. So this is a trapezoidal data map data structure. So let me just start this. And then we will take a break. Okay. So so that you can maybe during the break, spend some time to digest this. Okay. So this is a very special data structure. You can see that. Okay, is it a tree? This is not a tree, okay, because you can see, okay, at least you can see this leaf node F. It is pointed by two internal nodes, right? Which is not possible in a tree data structure, right? This data structure, we call that a tree-like graph. A tree-like graph. Okay? It's similar to a tree, but some endpoints, some leaf nodes may have more than one parent. May have more than one parent. Okay. How to use this one? How to construct this one? We will talk about this after the break. Okay.